Right now, you're holding a miracle, not a metaphor, an actual literal miracle. The device you're watching this on, whether it's a phone, a laptop, a tablet, has something inside it that is more complex than anything nature has ever produced on its own. The chip inside a modern smartphone contains more transistors, more individual electronic switches, than there are neurons in the human brain. We're talking 15 to 20 billion transistors on a piece of silicon the size of your thumbnail. And the crazy part, nobody on Earth fully understands every layer of how it's made. Making a single chip requires 25 countries, thousands of companies, machines that cost as much as a Boeing 737, and physics that operates at the edge of what's theoretically possible. And if one single company, in one single country, decided to stop selling one single machine, the entire global economy would start seizing up within 6 months. That's not an exaggeration. That's just Tuesday in the semiconductor industry. Today we're going inside the most important and most invisible industry on the planet. This is the story of how computer chips are made. The factories, the machines, the science, and the geopolitics that hold the whole thing together. Before we go anywhere, we need to establish one thing. What actually is a chip? Because most people have a vague idea. It's small, it's important, it goes in computers. But the specifics are where things get interesting. A chip, at its most fundamental level, is just a collection of switches. That's it. Tiny electronic switches called transistors. Each transistor can be in one of two states, on or off. Current flows or it doesn't. 1 or 0, yes or no. And from that stupidly simple idea, billions of ones and zeros, we get everything. Music, videos, messages, AI, banking, the entire digital world. The transistor was invented in 1947. It was the size of your palm. By the 1960s, engineers figured out they could stamp multiple transistors onto a single piece of silicon. That was the integrated circuit, what we now call a chip. The question then became, how many can we fit? And the answer, decade after decade, was more. Always more. In 1965, Gordon Moore, co-founder of Intel, made an observation that became a prophecy. He noticed that the number of transistors on a chip was roughly doubling every 2 years, while the cost stayed the same. This became known as Moore's Law. And for 60 years, the entire industry organized itself around making it true. Here's where the numbers stop making sense to human brains. A human hair is about 70,000 nanometers wide. The transistors in a modern chip are 3 nanometers. That means you could fit more than 23,000 transistors across the width of a single human hair. To put it another way, a 3 nanometer transistor is so small that it's only about 15 silicon atoms wide. 15 atoms. We are manufacturing at a scale where quantum physics, the weird, unpredictable behavior of matter at the atomic level, starts causing actual problems. Electrons start tunneling through walls that are supposed to stop them. The laws of physics are actively working against us. And yet, engineers figured out how to do it anyway. So how? Here's the first thing that surprises most people about chips. The companies that design chips are not the same companies that build them. Apple designs the chip inside your iPhone. Apple does not manufacture it. They have no factory. NVIDIA designs the GPUs powering the AI revolution. NVIDIA does not manufacture them. No factory. Qualcomm, AMD, MediaTek, same story. These are called fabless companies. Fabless as in no fabrication facility. They're brilliant design shops that outsource the actual making to someone else. Now, how do you design something with 15 billion components? You obviously can't draw it by hand. You use specialized software called EDA tools, electronic design automation. It's like AutoCAD, but for things that are millions of times more complex than any building ever built. And here's the geopolitically spicy part. This EDA software market is dominated by essentially 2 American companies, Synopsys and Cadence. Without their tools, you cannot design a modern chip. Full stop. China has been trying to build domestic alternatives for years. They're maybe a decade behind. So the very first step in chip creation, the design, is something the US controls almost completely. So you've got your design. Billions of transistors arranged in a perfect blueprint, all living inside a piece of software. Now what? Now you need to actually build it. And this is where things go from impressive to genuinely insane. Let me introduce you to a machine that most people have never heard of, but which might be the single most important piece of equipment in the modern world. It's called an EUV lithography machine. EUV stands for extreme ultraviolet, and only one company on the entire planet makes it. That company is ASML, based in Veldhoven, Netherlands. Population, 45,000. Yes, the city, not the company. Let's talk about what this machine actually does, because it's one of the most audacious things humans have ever built. Making a chip is essentially like photography. You're printing a pattern onto silicon. The pattern is the circuit, all those billions of transistors and the connections between them. To print features that are only a few nanometers wide, you need light with an incredibly short wavelength. The shorter the wavelength, the finer the detail you can print. EUV light has a wavelength of 13.5 nanometers. For context, visible light, the light your eyes can see, ranges from about 400 to 700 nanometers. EUV is roughly 30 times shorter than visible light. So how do you generate EUV light? You take tiny droplets of molten tin, each one smaller than the width of a hair, and you fire a high-powered laser at them 50,000 times per second. When the laser hits the tin, it vaporizes it into a plasma. That plasma reaches temperatures of 250,000 degrees Celsius. That's about 40 times hotter than the surface of the sun. And that superheated plasma emits EUV light. But here's the problem. EUV light is absorbed by literally everything. Air, glass, almost any material you'd normally use for mirrors or lenses. So ASML had to build an entire optical system out of polished mirrors in a near-perfect vacuum. These aren't normal mirrors. They're the smoothest surfaces ever manufactured by humans. If you scaled one of these mirrors up to the size of Germany, the biggest bump on the surface would be less than a millimeter high. The entire machine, which weighs 180 tons and is the size of a double-decker bus, has to be isolated from vibrations, including vibrations from people walking nearby, including the vibration of the Earth itself. It ships in 40 shipping containers, takes months to assemble, requires a team of engineers on site for the installation, and it costs $380 million per unit. There are roughly 200 of these machines in existence, scattered across a handful of facilities in Taiwan, South Korea, and the US. Every leading-edge chip on Earth, in your iPhone, in a data center, in an AI supercomputer, was made using one of these machines. And if ASML can't ship them due to export bans, geopolitical conflict, supply chain breakdown, the world's most advanced chip production simply stops. No backup, no alternative, no plan B. One company, one machine. The whole world depends on it. You've got your design, you've got the machine that can print it. Now you need a place to actually make the chips. That place is called a fab, short for fabrication plant. And the most important fab in the world is operated by a company called TSMC, Taiwan Semiconductor Manufacturing Company. TSMC makes chips for Apple, NVIDIA, AMD, Qualcomm, MediaTek, and hundreds of other companies. If TSMC is a country, it would be the world's most critical nation. But it's actually just a company. In Taiwan, let's go inside. The first thing you'd notice walking into a chip fab is that you cannot walk into a chip fab. These are called clean rooms, and they are the cleanest environments ever created by humans. A hospital operating room has about 100,000 airborne particles per cubic meter of air. A chip fab's clean room has fewer than 10 particles per cubic meter. That's 10,000 times cleaner than a hospital. Why? Because a single microscopic dust particle landing on a silicon wafer can ruin an entire chip or an entire batch. At 3 nanometers, a particle of dust is like a boulder crashing into your circuit. Workers wear full-body bunny suits that cover everything. Even then, the suit itself is filtered. Now let's talk about the actual process. It all starts with silicon, which is essentially very pure sand. Silicon is the second most abundant element in Earth's crust. We are not running out of it. The silicon is purified to an extraordinary degree, We're talking 99.9999999% pure, then melted and grown into a large crystal called an ingot. That ingot is then sliced into thin circular discs called wafers. A standard wafer is about 300 millimeter across, roughly the size of a vinyl record. Each wafer then goes through over 1,000 individual processing steps. It takes about 3 months to go from a blank wafer to a finished chip. Here's the basic loop, repeated many times. Step 1. Coat. The wafer is coated with a light-sensitive material called photoresist. Step 2. Expose. The EUV machine shines that extreme ultraviolet light through a mask, a template of the circuit pattern. The light changes the chemical properties of whatever photoresist it hits. Step 3. Develop. The exposed areas are washed away, leaving a perfect pattern in the photoresist. Step 4. Etch. Chemicals etch away the silicon beneath the exposed pattern, carving the circuit into the wafer. Step 5. Deposit. New materials are deposited to build up the next layer of the circuit. Then you do it again, and again, and again. A modern chip has somewhere between 50 and 100 layers stacked on top of each other, each one thinner than a human cell. When it's done, the wafer gets cut into individual chips, called dies, and each one gets tested. The ones that pass go on. The ones that fail get discarded. And the yield, the percentage that pass, is one of the most closely guarded secrets in the industry. On cutting-edge processes, a bad yield day can cost tens of millions of dollars. Here's something nobody tells you about the chip in your phone. Before it reached you, it touched at least 25 countries. Let's run through it. The silicon comes primarily from Japan and the US. The rare gases used in the process, neon, xenon, krypton, came largely from Ukraine before the war and from China. Ukraine alone used to produce 70% of the world's semiconductor-grade neon. The 2022 invasion sent shockwaves through the chip industry. The photoresist chemicals, the light-sensitive coating, come from a handful of Japanese companies, JSR, Shin-Etsu, Tokyo Oka. Japan has a near monopoly on several critical materials. The chip design tools? American. Synopsys and Cadence. The EUV machine? Dutch. ASML. The fab that actually builds it? Taiwan. TSMC. Packaging and assembly. Where the chip gets cut, tested, and put into the little black housing you recognize? Malaysia, Philippines, Vietnam, China. Final device assembly? Mostly China, with some in India and Vietnam. Every single link in that chain is a potential point of failure. One volcano eruption in Japan, one typhoon in Taiwan, one export ban from Washington, one border closure in Ukraine, and suddenly the global supply of chips gets constrained. And within months, cars can't be built, phones can't be manufactured, servers can't be shipped. We saw exactly this during COVID. A factory in Malaysia shut down. Car manufacturers ran out of chips. Ford, GM, Toyota. They all had to slow production. The shortage cost the auto industry over $200 billion in lost revenue. And that was during a relatively mild disruption. The industry has known about this fragility for decades. It's only in the last few years that governments started taking it seriously. Let me tell you about the most important war nobody's calling a war. It doesn't involve troops, it involves transistors. For most of the 1990s and 2000s, semiconductors were just business. Companies made them, sold them, the world bought them. Open markets, global trade, no big deal. Then two things changed. First, China got serious about technology. The Chinese government identified semiconductors as the foundational technology of the 21st century. Whoever controls chips controls AI, military systems, telecommunications, economic power, everything. Second, the U.S. noticed. In 2022, the U.S. government passed the CHIPS Act, $52 billion to rebuild domestic semiconductor manufacturing in America, which had shrunk from 37% of global production in 1990 to about 12% today. At the same time, the U.S. started restricting what chips and chip-making equipment could be exported to China. And in 2023, they pressured the Netherlands to ban ASML from shipping its most advanced EUV machines to China. China currently cannot manufacture chips below roughly 7 nanometers domestically. The rest of the world is at 3 nm and racing toward 2 nm and beyond. China is spending over $150 billion trying to close that gap. They've built dozens of new fabs, recruited engineers globally, and made chip self-sufficiency a national priority at the highest levels of government. But here's the brutal reality. You can't just throw money at this problem. Building a leading-edge fab takes 5–10 years. Training the workforce takes a generation. And the knowledge is deeply embedded in thousands of supplier relationships, material science breakthroughs, and process secrets that TSMC has refined over 30 years. Money helps, but it doesn't buy you time. And then there's Taiwan. Taiwan makes roughly 90% of the world's most advanced chips. Think about what that means. 90% of the chips that run AI, that run smartphones, that run military systems, data centers, financial infrastructure, everything. Taiwan is a self-governing democracy that China claims as its territory. China has never ruled out using military force to take it. The U.S. has a policy of strategic ambiguity. They haven't explicitly promised to defend Taiwan militarily. But here's the thing everyone knows but nobody quite says out loud. If China invades Taiwan, and even if they win, the war itself would likely destroy the fabs. TSMC has reportedly told the U.S. that it has measures in place to make its most advanced processes inoperable if it's seized. Capturing TSMC militarily would give China a pile of rubble and a skills crisis. So Taiwan's chip industry is simultaneously its greatest vulnerability and its most powerful deterrent. Chip people call it the silicon shield. It might be the reason there's been no invasion so far. So where does this all go from here? Moore's law, that doubling of transistors every 2 years, is running out of room. You cannot keep shrinking transistors forever. At some point, you hit the laws of physics like a wall. We're not quite at the wall yet, but we can see it from here. So the industry is pivoting. Instead of just making transistors smaller, they're getting creative about what you do with them. 3D stacking. Instead of spreading transistors flat across a surface, you stack chips on top of each other like floors in a building, with tiny vertical connections between them. More compute, same footprint. Chiplets. Instead of one giant chip, make multiple smaller chips that work together. Apple's M-series chips, AMD's latest processors, they all use some version of this. It's more efficient and dramatically improves manufacturing yield. New materials. Silicon isn't the only option. Gallium nitride, GaN, and silicon carbide, SS, are better for certain applications, particularly power electronics in electric vehicles and energy systems. AI chip specialization. General-purpose chips are giving way to chips designed specifically to run AI workloads. NVIDIA's dominance in this space made them briefly the world's most valuable company. Every major tech company is now designing its own AI chips, and demand is only going up. A single large AI model training run uses thousands of GPUs running continuously for months. The inference, actually running the model to answer your questions, requires entire data centers. The semiconductor industry isn't slowing down. If anything, AI has thrown gasoline on it. The global chip market was worth around $600 billion in 2024. Analysts project it to cross $1 trillion by 2030. So here's what I want you to take away from all of this. The semiconductor industry is simultaneously the most globalized, most concentrated, and most fragile critical system in the modern world. It requires the cooperation of dozens of countries, thousands of companies, and millions of highly skilled workers, all coordinated with a precision that makes rocket science look straightforward. One company in the Netherlands builds the only machine that can make the most advanced chips. One company in Taiwan does 90% of the world's leading-edge manufacturing. 2 American companies control the software without which none of the designs can be made. And somehow, despite wars, pandemics, supply shocks, export bans, earthquakes, and the relentless laws of physics, the industry keeps delivering. The chip in your pocket is more powerful than the computers NASA used to reach the moon. Cheap, complex, and built across the world, it powers everyday life. If this changed how you see technology, subscribe. We reveal the hidden systems behind the modern world.